Okay, thank you very much. It is a pleasure to be here. And today I'm going to discuss some progress, not just with my group, but our field, really pushing what we call first principles or ab initio nuclear structure calculations, first of all, towards really global calculations in nuclei, towards some of the heaviest nuclei that are out there, as well as exciting extensions towards really attacking some of the fundamental questions in beyond standard model physics where nuclei are relevant. And maybe to just piggyback on the discussion that we've been having, perhaps the future is a little closer than we think. And I would also like to highlight very strongly here the tremendous work that not only my postdocs, but students have done on this, really making this all work. Ragnar Stroberg and more recently Takayuki Miyagi, who came from Taka, and they've been doing fantastic work here. So I don't really need to introduce double beta decay. Of course, should it be discovered automatically, we have lepton number violation, game over. But of course, in sort of the absence of exotic new physics, we also have a path towards this effective neutrino mass, where in order to get there from some potentially observed rate, we need this nuclear matrix element. And since, of course, we have two unknown quantities here, this is something that can only be calculated within nuclear structure. It's not an observable, so it really falls on those of us in the field to do a good job here, and we've heard much discussion already. But even beyond here, we need reliable calculations of this matrix element simply to interpret the results of these large-scale searches, because of course, as the lower limit continues to increase on the lifetime of neutrinoless double beta decay, you kind of have this sort of moving down of these bands, excluding different regions of phase space here. But of course, the width of these bands is not some experimental uncertainty. It's our uncertainty and our knowledge of this nuclear matrix element. So, should our calculations or our results change, first of all, we might see some reduction in this band, but depending on if things move up or down, that could also shift this band up or down, so which could be good news or bad news depending on which way it goes, of course. So really, it's imperative that we do a good job, and of course, we see many variations of this plot, where there's typically a spread on the order of 2, 3, or a little bit more in different calculations of these matrix elements. But something I would just like to highlight here is really all calculations here, except for one new point, come from models, right? From different nuclear models. And of course, there's always some good physics within nuclear models. But everything here is missing some essential physics. And so we always hear disagreements of correlations versus the size of your single particle space, all of this. And furthermore, I think virtually everything here is missing, maybe one or two might have it in here, the effects of two-body currents, okay? So really, no good calculation is on this plot, where we have all the relevant physics to do a good job on these matrix elements. And furthermore, the difficulty or the problem with models, it is almost impossible, feel free to argue, to assign anything remotely like a rigorous uncertainty. So while we may have numbers, how much do we trust them? And so, well, ultimately what we'd like to do is, in order to provide something from our field for these billions of dollars being spent on the experiments, we'd really like to take a new approach to how we tackle these types of calculations, not just in neutrinoless double beta decay, but there's really an analogous situation in WIMP-nucleus scattering, where in order to, we've already seen several exclusion plots like this, in order to put the results of many of these large-scale searches onto one plot like this, we need to know nuclear structure. We need to know how the nucleus itself will react to some WIMP scattering event, and that is parameterized or captured here in this structure function, which again can only be calculated in nuclear theory, and to date has only been done within models, although some very nice physics has been put in. So that's where we'd like to go. And now how do we get there? When it boils down to it, all we're after here in this first principles approach is simply this, right? Of course, the full A-body Schrodinger equation, simple to write down, one of the most complicated or difficult problems in all of physics, because first of all, we don't even know the Hamiltonian. We don't have some rigorous connection between the fundamental theory of the strong interactions, QCD, to the energy scales that are relevant in nuclei. So we don't have this rigorous connection. But what we do is we have a fantastic tool that's being developed very rapidly in the community called chiral effective field theory, which, not to get too technical, is just simply a low energy expansion of QCD, where 2, 3, and higher body forces arise naturally within the theory, as well as consistent electroweak currents. So this is really kind of a breakthrough in really how we're able to handle nuclear forces and electroweak forces in a consistent manner. And if this is done correctly, which is, of course, this is really one of the points that's being worked on in the field, if this is done correctly, then in principle, if we know sort of the expansion parameter here, we can estimate then the physics that's being neglected when we truncate this at some given order. So what this means is, in principle, we're able to put some rigorous uncertainty estimations on nuclear interactions and electroweak interactions. Now, the reality is, of course, much more complicated, but in principle, that's there. So now, even if we know perfectly these interactions, strong electroweak interactions, we still then need to deal with the nuclear many-body problem. So we need to solve this eigenvalue problem, which, if we had a big enough computer, this can just be done. Even with the biggest computers, we've seen really over the decades, the progress has been very slow, because ultimately, to calculate something like energies, you really need to take into account all particle hole excitations into essentially an infinite single particle space, and this grows combinatorially. So since computing power typically grows exponentially as well, that we've seen a rather slow increase in the type of converged nuclear physics calculations that can be obtained in this sort of first principles approach. But over the past year or decade or so, there's been really a flourishing in new many-body approaches, which are not quite as exact, but nonetheless, they're systematically improvable, controlled, and in principle, we can also think about putting some sort of uncertainty estimations on the end results, where we've really seen an explosion in the reach of ab initio theory. This has really took place over a few years, and notice this plot is already several years old, and if we were to update it to today, we're already really to scale off of this screen, because very recently we've been able to obtain really converged calculations in the tin 132 region, and we're even potentially pushing towards lead. But just because we can go to these heavy systems doesn't mean that we can tackle everything in between. And so this has really been where a lot of the work in the field has been heading, really thinking about extensions of these ab initio many-body methods to improve the reach, because they work typically extremely well at doubly magic systems, but they're always non-trivial extensions to go beyond that. But what we don't have is a method that really can cover all nuclei, and that's where my group comes in. Just very quickly, the method that we use is called the valence space in medium similarity normalization group. Don't worry about ever repeating that. But what it is simply a clever way to construct a unitary transformation where step 1, we define some core, just like in the usual shell model picture. But step 1 of this transformation decouples this core from all particle hole excitations. And so that's exactly, if you kind of transform to a new picture where all of these excitations are 0, your ground state, your new configuration, is a fully correlated ground state. So that's, of course, in the situation of a exact unitary transformation. We do have to make approximations along the way, otherwise we're solving exactly the many-body problem. And that comes into truncating certain operators at the 2-body level instead of 3-body level, but that's a bit technical. If you want to know more, please ask me. Step 2 is then we decouple some block Hamiltonian from the initially very large single particle space, Hilbert space, where we essentially decouple then something that looks like a shell model Hamiltonian, except, again, since this would be a unitary transformation, when we diagonalize this much simpler problem, this would then give us some subset of eigenvalues of the full many-body problem. Again, since we make truncations, this won't be exact, but we can gauge how well we're doing compared to other large space methods, like couple cluster theory and other things that we've heard about. But what makes this approach so powerful is once we have this unitary transformation in hand, we can apply it then to any operator, not just the Hamiltonian. So immediately, we're able to calculate pretty much anything that could be calculated in the shell model framework, but from an ab initio perspective. So any operator you want, charge radii, electromagnetic transitions, gamma of Teller, double beta decay, WIMP-nucleus, whatever you have. If you have an operator, you can give it to us, and we can treat it in an ab initio fashion. But, of course, we always have to benchmark against large space methods where we know, things like couple cluster, where we know they're extremely accurate because you never know exactly how different treatment of operators will be manifested. So the first thing that, of course, we wanted to benchmark is energies. And starting from some set of 2 and 3 body forces, this is something that my postdoc, Ragnar Stroberg, really changed everything here, where we really showed that, for instance, in the absolute ground state energies of the oxygen isotopes, or whether we're talking about calcium isotopes, we really agree with the best other many-body methods on the market to the level of 1% or better, including quasi-exact things like no-core shell model. Of course, there are fewer methods up in the calcium region, but nonetheless, we agree extremely well where they can calculate, and then we can essentially take it, cover everything from there. But what you might notice here is that, okay, from this particular set of 2 and 3 body forces, which do well in oxygen, ridiculously overbind the calcium isotopes. So while we agree with these other methods, if we don't have a good starting Hamiltonian, then we're not going to be doing a good job reproducing experiment or predicting experiment. But it turns out that over the past couple years, we really discovered that we had in hand something that is almost magic here. Because there's one set of 2 and 3 body forces, which if you just look at the energy per particle, starting from helium all the way up to nickel, 78, is really nailing the ground state energy per particle. And this is unprecedented in nuclear theory to have an interaction that reproduces energies, as far as we know, all the way up the nuclear chart. And so now if you combine the fact that we have a method that can essentially calculate anywhere the shell model can in an ab initio way, plus an interaction that looks to be doing a very nice job, at least on energies. The other operators we still have to check, and we can have that discussion. We can really go from a picture like this in calcium to a picture like this, and really then globally extend ab initio structure from something like this to really really blanketing the chart anywhere the shell model can calculate, where the only limitations here are computational. So at the endpoint, we do still have to do something like a shell model diagonalization. So when we get into this region, that's, of course, difficult, as we saw from Taka. But also, the other limitation has been really simply storage of all of these 3-body matrix elements. And that was really our limitation around TIN 100 as of a year or two ago. But my new postdoc, Takayuki Miyagi, really made some incredible advances here, really allowing us to not only go to TIN 132, but maybe even towards the lead region. So we can now really address in an ab initio way fundamental questions in nuclear structure, including something like this. How heavy can we go? And just to flash some very quick results, we can really calculate the ground state energy in lead, and it's looking to agree very nicely with experimental values. It's not fully converged, but this is something that we're really working on, and should hopefully within the next several months or year really pan out. But again, I don't want to spend too much time on the structure aspects. I want to get to the double beta decay and such. But also, very briefly, something very nice that we've done is really undertaken a global calculation of essentially all nuclei up through the nickel region. Really 700 were calculated from this nice interaction that does a good job on energies. And here we have really the residuals in absolute ground state energies across this range. And what you see is quite remarkable, that with this interaction, we have an RMS deviation from experiment of 3.3 MeV. And that is comparable to things like the beta-Weizsäcker mass formula. And again, absolutely no input is going into any of these calculations beyond 2, 3, and 4 body data that's needed to constrain these chiral interactions. So these are pure predictions across the chart and appear to be doing very good. So if we're doing that well on ground state energies, we're doing actually even better on separation energies. So I'm just going to go quickly through this. But a very nice first sort of study that we did here was really mapping the proton and neutron drip lines all the way up through this the nickel or iron region. and finding extremely nice result, agreement with experiment where it's known on the proton-rich side, and making predictions here for rare isotope facilities on the neutron-rich side. Okay, so that's, if you want to know more about that, please come up and talk to me. There's many, many things that we've done on the structure side, but of course, what we're interested in is this beyond standard model physics, and so things like double beta decay or WIMP-nucleus scattering. But before we can begin to talk about double beta decay, we need to talk about single beta decay, and this is where the point in the talk where it could get a little uncomfortable because, yeah, I think we need to talk about GA quenching, okay? So we've heard many discussions, and I think it's mostly a matter of language, but I think that language can lead to some very misunderstanding and misinterpretations of what's really going on and what should be done in not just calculations, but in interpreting different things. So what is GA quenching? So of course, it is a long-standing problem, and you know it's a long-standing problem when papers from the 70s say it's a long-standing problem. But ultimately what it is when we try to calculate Gamow-Teller transitions across a range of nuclei, what we see is our calculations do not agree with experiment. They don't line up. And they're off really systematically here by some, if you just, this is the SD shell, you have the exact same picture in the PF shell. They're just off. So, of course, if you kind of take the slope here, multiply by that, of course, magically, everything looks great. Not magically, you tune that. And so what are we really thinking? And so what we often see is that, okay, this is interpreted as some effective quenching of this fundamental coupling in nuclei on the order of 0.75 to 0.8, depending on which region. But what we're really plotting is this, and so we're really shuffling this discrepancy into GA. But it never made sense to me why we would do that, because in this calculation we have this, which is incredibly difficult. This is, one of the, there's so much that goes into this, so it never made sense why we should talk about quenching GA unless we're doing a good job calculating this. Unless we know we have all the relevant physics in this object, then we can start thinking about it. So all we're essentially doing is parameterizing our inability to do a good calculation, but that's not really saying something about this fundamental coupling. It's just saying we're not doing a good job here. So to really address this issue from really a first principles perspective, a group of us, several different collaborations got together to join forces to really attack this problem. And so what we want to think about is what is all of this other stuff and what could potentially be difficult to calculate here. So first of all, the wave functions. We wanted to treat the wave functions in an ab initio perspective, so that means starting from 2 or 3 body forces from chiral effective field theory, and doing as good of a job calculating these initial and final states as possible. Step 2, since these are usually done in a shell model framework, often, or almost always, there's never some treatment of a consistent effective valence space operator here. So of course, you can have a Gamow-Teller operator mediating physics outside of the valence space, and so we want to then derive a consistent effective operator consistent with the Hamiltonian. Of course, that's almost impossible to do in any phenomenological way. And finally, the sigma tau operator is only the leading order in Gamow-Teller transitions. We know that there will be subleading order, two-body effects, currents, Jesus, that's what I'm trying to say. Two-body currents, where this guy is capturing the effects of pion exchange, and here in this contact interaction, we have more heavy meson exchange that are outside sort of the chiral effective field theory. And so only once we take into account all of this physics, look at our results, then we can start to say something about what we should do with GA. And so this is something that a group of us did. Really, there were, it's a very nice kind of write-up here in Nature. We're showing in orange all of the different nuclei that we calculated in this study, where we had at the very light region, no core shell model, which is essentially exact results. And we were always careful to benchmark whenever we could between our methods and no core shell model. A couple cluster theory, which is the gold standard for doing a doubly magic nucleus, tackled some extremely heavy cases, including tin 100, which is the largest known Gamow-Teller matrix element out there. And then we covered really everything in between with our valence space in medium SRG approach. And the results, really from the light all the way up to tin, were remarkably consistent. So if you hear just the results in the light region, again, just sort of looking at the effects of two-body currents, kind of take you typically closer to experiment. And if we just had to come up with a quenching factor for these green dots, it's on the order of 0.95, 0.96, something like that. So no need for quenching. Going to the very end of the study, in the heaviest tin 100, couple cluster, first of all, going from sort of extreme single particle model to these open circles is the effects of correlations, and then going from these open circles to the filled in ones, symbols to the filled in ones, is the effect of two-body currents. And again, so we started from as wide of a range of input 2, 3-body forces and consistent electroweak currents as we could think of. So this is some level of a uncertainty at this level. But again, comparing with the nice new measurement that came out of Japan this last year, again, if you're to assign a quenching factor, it's on the order, maybe 0.9-ish or something. So again, not the typical 0.75 that we're used to seeing. And picking one particular interaction, although we studied several, we just saw this plot a few minutes ago. Really in the SD and the PF shell region, without the effects of either this renormalized operator or electroweak currents, where we have this orange band, and when we include really the physics that we know should be there, we have this green, and here in the SD shell, the quenching would be something like 0.96, here's something like 0.92. So really across the chart, we're seeing a consistent effect of correlations and currents such that in the end, you don't need to have much of anything like quenching here when we're using the standard 1.25 for GA. And of course, this shouldn't be perfect. We know there are improvements that have to be made. The chiral interactions, we need to go to subsequent orders, things like this. So we shouldn't be doing a perfect job yet, but nonetheless, this looks to be really capturing the physics that's relevant for quenching. So now we can start to think about really moving to other problems, such as neutrinoless double beta decay. Let me just skip the 2 neutrino. The first step was really now, if we trust single beta decay, how well do we trust double beta decay? Because of course we have, these are different operators. So we benchmarked again in light systems. Here we have helium, helium-8, helium-10, carbon-14, and oxygen-22, which would be the analog in the SD shell of calcium-48. And here, we're really comparing our in-medium SRG approach to no-core shell model, and whether we're looking at the Gamow-Teller, Fermi, or tensor part, we really have a remarkable agreement with these quasi-exact results. So that means that we would then have some confidence in pushing towards the heavier cases. And so here, in calcium, really just focus on the upper left plot here. This is just Gamow-Teller, Fermi, tensor. So using this interaction that does very nicely with energies, we have these blue points where these are increasing the size of our single particle space. And so we see we're very well converged by the time we're here. Also using another interaction that Peter Navratil had developed, we see that, again, very nice convergence and a very modest, it might look like a big spread here, but if we go to this scale, this is a very modest difference between two input Hamiltonians. That's some level of uncertainty. And then very nicely, there was a beautiful calculation done by Heiko Hergert and Jiangming Zhao and John, starting from the same interaction, but a completely independent many-body method, and they come with a band something like this. And this is what you would expect to see from ab initio theory. Starting from the same point, two calculations should agree within uncertainties. And so that's what we have for calcium. But the nice thing with this valence space approach, like I said, is we can really go anywhere the shell model can. We've recently extended these calculations to germanium-76, where we see we're extremely well converged with these two interactions. And again, putting those 2 points on this plot is something like this. Going to selenium-82, again, similar thing, very well converged. And again, coming in at really the lower limit of this band. And very recently, because of this fantastic work that Takayuki Miyagi has done, we've even been able to go to tellurium-130 and xenon-136. Not completely converged, but this red band would be kind of our best calculation. and going between these. So it's pretty much looking converge in this direction, and going from here to here is kind of the improvements that he's making, and we can go several steps further now. But nonetheless, oh yeah, these scales are totally different, so this looks worse than it actually is. But nonetheless, we have this, and it's really a matter of not too much time before we should be able to have really converged calculations here. And again, these are really on the low end. So let me just kind of stop there. We also have very nice results for WIMP-nucleus scattering, really going from the nice work that Javier and Philip Close and Achim have done in Darmstadt several years ago, to really treating this in a fully ab initio fashion and seeing some slight changes in the results, but nothing too dramatic. But I will just leave it there. And here is my next 10 years, or hopefully 5.